All right, so thanks. So the organizers of the DENESC program asked me to give this kind of overview talk, I guess targeted at also the other program on integrability, but to the broader KITP audience. So I chose a kind of very general title, but I'll try to talk about something relatively concrete. So my title is Interactive, quote-unquote, Many-Body Quantum Dynamics, and I'll spend some time in the beginning of the talk explaining precisely what I mean and why we think it's interesting. So in a nutshell, I'll be thinking about many-body quantum systems and some very general type of dynamics, probably the most general type, where you not only have unitary evolution from quantum mechanics, but you also allow yourself to interact with your system. Okay? And by interact, I mean through, for example, measurements. Since this is quantum mechanics, measurements are non-trivial. Okay? And you can also use the measurement outcomes to kind of affect the dynamics after this. And I'll explain the type of questions we're thinking about in that context. So before I start, I listed some references. This is a chalk talk. I won't be citing people appropriately, so I apologize in advance to all the experts in the audience in particular. I did list 2 reviews on top that are especially useful if you're interested in this topic. One that I wrote with Drew Potter, which has more of a statistical physics feel, which maybe would be nice for the integrability folks in the audience. And there's another very nice review by Vedika, Matthew, Sagar, all of whom are in the audience, and Adam Nahum. Okay, so if you're interested, I strongly recommend you have a look at those reviews. I also listed some questions that I find interesting. This is not an exhaustive list, but they're related to what I'm going to tell you about. And the goal in this talk will not be to answer any of those questions. I actually don't know the answer to many of them. I have some things to say about some of them, but rather I'll try to motivate why we are thinking about those questions and why we think they are interesting. Okay. All right, so let me get started by kind of defining more precisely what I mean. So like many KITP programs, I guess we have a very broad, it's a broad audience with many communities with different perspectives. Some people working on quantum error correction and more quantum information science topics, and we have some people like myself more on the quantum dynamics side. So I'll be taking the perspective of quantum dynamics in this talk, but I'll try to connect to the other topics. So let me start by kind of defining what I have in mind here. And I'll do this in some slightly pedantic way by just breaking it down into 2 pieces. Okay, starting with quantum dynamics, just to make sure that we're all on the same page. So this is not a particularly new topic, but it's still relatively new, at least in the way I'm going to define it. And I think the best way I can define what quantum dynamics is by defining it in contrast with maybe standard many-body theory or solid-state physics. So in traditional, condensed matter physics, we're typically interested in a system that would be in thermal equilibrium. And if we're interested in universal, maybe quantum properties, typically we would want to be at very low temperature. And if we want to maybe probe our system and we want to think of dynamics in this context, it would be something like linear response. Okay, so you weakly perturb your system and you see how it reacts. Okay? So this is not what I'm going to talk about today. Okay? And the quantum dynamics that I'm going to talk about has a very different type of setup and experiments in mind. And so this is a field that was largely driven by the advance of analog quantum simulators, such as cold atoms, trapped ions, arrays of Rydberg atoms. So systems in which that are pretty well isolated from their environment, and over which we have some control over the interactions, and we can kind of realize some specific Hamiltonians. And the type of setup we have in mind here is something where you imagine you start from an initial state that you can prepare pretty well. For now, we'll assume it's a pure state. And very generically, we're just going to meaning that we can prepare this initial states and then time evolve with some Hamiltonian over which we have some good level of control. Okay? And think of this dynamics, and at the end of the day, we make some measurements. Okay? And so here I'll assume that we're dealing with some maybe isolated system, but of course you can maybe generalize this to thinking that maybe you can have a periodically driven system, those are called floquet, where you can think of the role of the environment, and I'll talk about this in a minute. Okay? All right, so this is a very general setup, right? This is basically just solving the Schrödinger equation for a system with many particles. So why would you do this? It seems like it's a question that's almost too general, right, to be interesting. And the guiding principles that people have used has been to kind of look for universal phenomena in this dynamics. So it might sound a bit counterintuitive that you would have anything universal about this. Okay. There's nothing low energy about this. This initial states will generically be a very high energy state with respect to that Hamiltonian. There's no low energy physics, not coarse graining anything. But nevertheless, over the years, we've learned that there are a lot of things that are universal about this. And so in particular, you can ask the same type of questions we ask here, the type of phases of matter you can realize in that setup. Okay. So one other key guiding principle has been the notion of thermalization. Okay. That at least for most systems, generic systems with local interaction, even though they are isolated, they will eventually reach equilibrium on their own if you ask about local observables. So it's a bit subtle the way it happens, but relatively understood by now, at least at the big picture. Your full system is still in a pure state, but if you think of local observables, they kind of forget what the initial state is. Okay, so this kind of brings you back to that, though. Okay, but there's still interesting questions about how this happens, related to, notion of many-body quantum chaos, emergence of hydrodynamics from purely, quantum mechanics like that. Okay, and of course, if you have like a rule, you try to find exceptions, and in some of those exceptions, you can get very interesting universal physics. Some keywords that you might have heard would be many-body localization, MBL, if you have strong disorder related to the other program. You could have a system that's close to integrability. You could have many conserved quantities that will impact the type of state you get at long times and also the relaxation. You can have, recently people talk about scars and so on. I won't go into the details here, but the kind of systems that will escape thermalization one way or another. Okay. All right, so this is my lightning introduction to what quantum dynamics is. And so one thing I want to say is, among the tools that people have been using, many of them have been kind of borrowed from quantum information. In particular, the notion of entanglements turned out to be very useful to think about questions related to thermalization. Okay. So in particular, the notion of entanglement entropy is closely related to thermalization. Thermalization kind of tells you that if you take your system, drawing it here in 1D, and you take a subregion A, even though your full system might be in a pure state, if you look at a reduced density matrix over that system, at long times, this will effectively become thermal. This can be mixed, and this will effectively, with some temperature that's determined by your initial state. Okay. And you can compute, say, the entropy of that reduced density matrix. It's known as entanglement entropy. And it can be used to kind of distinguish those cases. Okay. All right. So what about interactive, which is really the kind of key ingredient I'm going to try to talk about today. So this is partly motivated by the advent of the NISQ era, which is, like, I guess in the title of the program, a noisy intermediate scale quantum devices, and kind of taking advantage of like the type of operations that would be native to those devices, at least in the near-term future. So here we're going to slightly, well, not slightly, we're going to generalize quite a bit the setup that I had here. I'm still going to think that I have some part of my dynamics which is unitary. Okay. But even that dynamics I'm going to try to consider as a bit more general than this. So rather than a system that has a Hamiltonian, we'll think a bit more generally we can apply arbitrary unitary gates, and we have a lot more control over that dynamics. So this dynamics will be digital or gate-based. So this is not the biggest difference compared to this, but this will have consequences. So we imagine that we can really realize arbitrary type of unitary evolution. Okay, and I'll give examples. But in practice, it means I won't have a Hamiltonian kind of doing discrete time unitary operations. And so on top of this, we'll imagine that we can monitor our quantum system. So we have an observer that can make measurements on that system. Since this is quantum mechanics, again, this act of measuring is non-trivial, right? And I will assume I can do those measurements as the time evolution evolves. So mid-circuit measurements. And so here I will have an observer that will collect some measurement outcomes. I will call them M, from monitoring the system. And based on those measurement outcomes, you're also allowed to have some feedback on your system, that is change the type of unitary evolution and maybe where you would have measurements as well. Okay? So you can change the dynamics of the system. Maybe you can perform some classical computation, maybe quantum, but okay, let's imagine you just have a classical computer. I can use those measurement outcomes to maybe do something to my system as well. Okay? And on top of this, because the systems are noisy, we'll add some environment here over which we don't have a lot of control that will lead to decoherence and dissipation. Okay? So this is kind of a very general setting of an open quantum system. I've highlighted some difference between observer and environment. Maybe it's not obvious to you why those are not exactly the same. Maybe you can think the environment is effectively measuring the system in some way, right? But you'll see, hopefully, in this talk that there's quite a distinction between knowing the measurement outcomes versus not knowing them. Okay. And the type of questions, so this is very general, but the type of questions that I'm going to be asking is, as a many-body theorist, is kind of inspired by the same type of questions I would be asking here. There's the type of phases of matter that you can realize in this setup. Let's say you have a system where you can kind of engineer some unitary evolution. You can monitor your system as you want. You can maybe perform feedback. What type of dynamical phases of matter does that buy me? Can I stabilize some new interesting states of matter? And once I have those states, maybe I can also have phase transitions. The same type of questions you would maybe be asking from more standard many-body physics. Okay. Any questions so far? Yes?
I have a question with respect to this.
Yes.
So, in general, you could also use the principle of deferred measurements.
Mm-hmm.
And get rid of the observer, but then what you'd be saying is there's no observer, but now you're interested only in a subsystem. Mm-hmm. And anything you want to say about phase transitions, etc., you want to say about that subsystem. So is that correct?
So here, I will really want to think that I'm doing mid-circuit measurements and that I'm possibly also acting right after the measurement to change the state of the system, at least in a very general way that I'm defining. Then you could imagine maybe more practical things where you defer the measurements and the type of, but in general, I would imagine I'm actually just doing the measurements as I go.
Yeah, but in fact, is it correct that anything you think about here would also happen if you just say, well, it was just an isolated system? And
in principle, yes. Yes, that's right. Yeah, in principle, you could think all of this is one big quantum system, but yeah, I will actually imagine that those are separate here. That's right. Because the environment, everything you could imagine is one big quantum system, but yes. Okay. Any other question? All right. So let me be a bit more concrete. And so today, at least for now, I'm mostly going to talk about just unitary evolution and adding measurements. Okay. I'll come back to feedback and environment, at least in the end. But for now, we'll just see that with those two examples, I can already get something quite interesting. So this brings me to this topic of monitored quantum circuits, also called measurement-induced phase transitions. So those are the only two references I'm actually going to quote in this talk. Leach and Fisher and Skinner, Room, and Nahum. So one of the groups was here, Matthew's group. And so let me introduce the model that they considered, okay, and illustrate how it fits what I just told you over here. So, okay, so I have a system that I'm going to take to be one-dimensional. Okay, so I have a bunch of qubits in 1D. So my Hilbert space is C2 to the n. So I have n qubits in 1D. Okay. So this is my space, and this is my time, quote unquote. Okay. So the time evolution has two ingredients, okay, in this model. So I'm going to think this part of the dynamics is just unitary dynamics, and we're going to take it to be very generic, and we're going to be applying a quantum circuit, which I have drawn here, which is random. So I have this brick wall pattern. Each rectangle here is a unitary gate that acts on nearest neighbor qubits. Okay. So this is just a 4x4 unitary, and we'll take those gates to be random both in space and also in time. So why are we doing this? Well, there are several ways to kind of motivate this. One way is kind of inspired by random matrix theory, I guess. We're trying to come up with a kind of a general time model that only captures what we want. So here what we want is to have quantum dynamics, which is kind of generic enough, and have local interactions. Okay, so what's local about this is that those gates only act on nearest neighbor qubits. Okay, so I don't have one big unitary that scrambles everything. Because I have this brick wall pattern, the interactions remain local. Yes?
If you're inspired by random matrix theory, then you don't want locality necessarily, right?
Yeah. So this is one step on top of random matrix theory in the way I see it, right? So I want unitarity in my time evolution because it's quantum mechanics, and I want to add locality, but that's all I want. Then I want a model that's as featureless as possible. And so it's fairly natural then to imagine let's make everything else random. And so I don't have any conserved quantity here. I don't have energy. I don't have a Hamiltonian. But I still have quantum evolution. It's still unitary. And interactions are still local. Okay. So again, I don't have a Hamiltonian. Time is discrete. You can think it's kind of the depth of the circuit where you keep applying it, and you can think of it as discrete time. Okay. So this is what I'm going to call just chaotic dynamics, right? And the claim is that we're just going to add one more ingredient, and that will already give us something very interesting. And these other ingredients are just measurements. Okay? And the claim is that this leads to some interesting phase transition in the entanglement structure of the system. So, okay, so the other ingredients are like those purple circles. And what those are just, at those points you just measure the states of those qubits in, say, some computational basis, like in the Z basis. The basis actually doesn't matter because you have those random gates. But let's say you take just natural basis and you just measure whether that qubit says up or down. Okay? And you do this with some probability P at each time step and each site. Okay? Okay, so P is kind of like a rate of measurement. So if P is 1, you measure every single qubit at after every single layer of gates. If P is 0, you just don't measure. And so when I say measure here, okay, so very importantly, again, this is quantum mechanics. So you're projecting the wave function onto the outcome of your measurement, say whether you're up or down. I'm going to call pi m the projector here. So this wave function is not normalized. If you want to compute anything physical, you should normalize it. Okay, it's just the usual measurements you learn about in quantum mechanics. And of course, they occur with the so-called Born rule. So the probability to observe a given measurement is just the norm squared of my wave function, the way I wrote it. Okay. So there are projective measurements. You could replace them by weak measurements, but it doesn't really matter. So let's assume we have projective measurements like that. Okay. And go back here. So it's a very, deceptively simple model. It only has two basic ingredients: quantum evolution and local interactions and measurements. Okay. And what those papers argued, based on intuition and partly on numerics, is that they should have an interesting phase transition only from those two ingredients. Okay? So you can imagine that then even adding more ingredients, you'll get even more interesting answers. So that phase transition is a bit subtle, and hopefully I'll manage to explain some of those subtleties. So the claim is as follows: you can follow your system in a so-called quantum trajectory. So that is, you think of your system, which is always in a pure state for some history of those measurement outcomes. So you find the first spin, you measure it, maybe it's up, second spin, maybe it's down, and you keep kind of evolving like this. And you imagine your system, you record those measurements, and your system remains in a pure state where you're labeled by those measurement outcomes. And the claim is you have a phase transition between different regimes of entanglement scaling. And if you don't like entanglement, I'll give you other interpretations. Because you have two things that compete with each other. So the first one is you have this chaotic dynamics from the random circuit. And this will tend to just increase entanglement in your system. So the way you can see this is even if you start from a product state, which has zero entanglement, if you consider a subsystem, I'm going to call it A, a bunch of my qubits are taken together, and if I form the reduced density matrix of my system in A, I start from this state, I trace over everything that's not in A, I guess a reduced density matrix, and I can compute. So this will be mixed in general. I can compute this von Neumann entropy, so that's entanglement entropy. As a function of time, if you don't have measurements, you would expect that this should, thermalize. And here, thermalization, you have no conserved quantity, so it basically means that your system is going to be maximally mixed or random, right? So there's nothing conserved in this time evolution. And in fact, so, the entanglement entropy in those systems you can actually compute exactly. So it grows linearly with time, and eventually it just saturates to something extensive, which is known as volume law entanglement. Okay. So one thing I should say here, so there are really two types of randomness, and it's really crucial to distinguish them. So there's some stochasticity from the measurement outcomes. This is really crucial to the physics. And there's some randomness that I kind of put because it will help me. I chose those gates to be random, and so there's some randomness over those gates, and this will be some inspired by, if you want, by statistical physics, where if you take an ensemble of systems, that will actually help you to make predictions. Okay. So this is a mixed state. It has volume law entanglement. And the claim is this actually persists even if you put in some measurements. Okay. On the other hand, the measurements will tend to reveal information. And as such, they will actually tend to lower your entanglement. So one way you can see this is if you take your Bell state of two entangled qubits. If you measure the first qubits, you'll project your wave function onto a state that's classical and that has zero entanglement. So you start with an entangled pair. If you measure one qubit, you will lose that entanglement. And so in general, if you take, you can see, for example, that if you take p equals 1, you measure every single qubit in your system. At every single time step, you measure the first qubit, it's up, the second qubit, it's down. What you get at the end of the day is a classical state that has 0 entanglement. But the claim is you actually have an interesting phase transition between a regime where you have this volume law scaling. If you don't measure enough, but there's a threshold over which the entanglement will just be area law. So here in one, it would be a constant. So there's a low amount of entanglement in your system. So it's a very fundamental phase transition. I'm talking about those trajectories. I'm saying they have very different type of entanglement, only having measurements. And again, it's a very generic system. So you would imagine that only adding ingredients like symmetries or more complicated type of measurements can only enrich that phase diagram and have even more phases and more phase transitions. And that's indeed the case. Okay. Of course, if you have a phase transition, it becomes pretty natural to ask, okay, what is that phase transition, right? Do you have universality? Do you have critical exponents? What type of phase transition it is? And it turns out to be a very hard question, but maybe relevant to, again, integrability people in the audience. It turns out to have some emergent conformal invariance. Okay, so it's a conformal field theory, that part we know, and it turns out to be kind of unpleasant type of conformal field theory, which is logarithmic or non-unitary. And I'll maybe say hopefully I'll get back to this by the end of the talk. Any questions so far? Okay, all right. Okay, so why do we think this is interesting, and why is it subtle? Okay, so why it's interesting? So it sounds to me, when I first saw this, I was very surprised. Again, because you have very minimal ingredients, it sounds like a very fundamental type of phase transition that people only realized very recently. I like phase transitions. That's all. I have some bias for phase transition and universal phenomena. And then it became also natural to think about, what is that phase transition and what type of behavior do we have? There's no obvious order parameter or symmetry or anything like this here, right?
Perhaps to ask a question. So,
yes.
This type of problem you can do basically for any circuit, right? So, you
yes.
put in the measurement, etc. And then
that's right.
The question is how general this type of phenomenon is. Is it randomness, the crucial part, or can you do other time evolutions?
Yeah, so
time evolution plus the measurement or something.
Yeah. So this is very general. So people try different type of gates, different type of circuits. You can fix the gates and still get these transitions. You could do specific types of gates. You can, again, add symmetries. So this is very general. If anything, it becomes richer if you, again, add symmetries or you add different type of measurements. You can, break up those two phases that I have into subphases. So you can only get like a richer phase diagram. This is kind of this was kind of the original story in those two papers that you can then kind of enrich. Okay. But the randomness from the measurement outcomes is kind of trivial. So it's kind of very important. So that I will emphasize. Yeah.
What about the dimension? Is it,
yeah. So this also works in higher dimensions. It's been less studied, but they are higher dimensional versions.
there is also a transition.
Yes, that's right. Yeah. Well, okay, I don't know how much people have probed. It's harder to do numerics in those higher dimensional systems, but yes, we believe there's certainly a transition in higher dimensions as well. Mostly this has been done in 1D because it's easier to do numerics. Let me mention just different interpretations of that transition and then kind of emphasize why. Again, it's maybe more subtle than it appears, at least in the way I presented it. So over the years, people came up with many interpretations of like what this transition is about. So I won't go into the details of any of them, but let me kind of sketch them briefly. There's a sense in which you can think of that transition as kind of a hardness transition in like simulating open quantum systems. And contracting some type of tensor network. So this is more of a complexity point of view, if you want. And in fact, similar ideas have been used in that field. There's a so-called purification perspective that I won't go too much into the details. You can change your initial states and choose a state that's initially not a pure state. That would be a mixed state. And it will remain mixed in one phase, and the measurement will kind of purify it in the other phase. A related interpretation, which I will say a few more words about, is related to a more quantum information perspective on that transition. So there's a sense in which this is a very, it's a fundamental transition that has to do with the amount of information you actually extract from your measurements. So in this phase, the mixed phase, the volume law phase, when you have weak measurement outcomes, the measurement records are kind of random unless you actually record your system for exponential times. So basically, if you want, the observer is actually not learning about the initial state by doing those measurements. That's one way you can understand those results. And the reason this happens is that the quantum dynamics is able to hide the information about your initial state into highly non-local degrees of freedom that the measurements cannot access. Okay? So physically, this is a bit related. So this is a phenomenon known as scrambling, which is related to thermalization. Right? So your system had some information, right? So it's, there's a lot of information in your state. But we said at long time, if you look at a reduced density matrix, like at a subsystem, you only know so much. Actually, essentially, you forget everything. Okay? And for similar reasons, the measurements cannot really, by making a low density of those measurements, you are not actually extracting meaningful information about your initial state here. On the other hand, in the other phase, you are extracting some information, at least with the initial measurements, about your initial state. And at long times, your system is actually determined by recent unitaries and measurements. Okay. So there's a sense in which this volume law phase is a good encoder of quantum information. There's a protected space where your information can live, and it's protected by the measurements. Okay. So this is some type of quantum memory, if you want, and decoding it is hard, and maybe we'll talk about this just in the discussion. Okay, so with this, there's one very important point that I should emphasize, which is going back to this picture I had here and the difference between measuring and having the environment. So it's very important in this transition that you actually record the measurements. And this is where, hopefully you'll see what I mean when I say it's subtle. Okay, so it's subtle because you could imagine, okay, what if I throw away my measurement records? Okay, what if I don't know what the measurement records are? And what it means formally is you now have a mixed state where you sum over all the measurement outcomes that you had in your system. Okay? So this is what you could imagine what the environment would be doing if it's measuring, but you don't know what the outcomes are. So the subtlety is that if you look at this density matrix now, which is a classical superposition of those measurement outcomes, you actually have no sign of that transition. So that transition is only, so everything depends on time here, that transition is only in those trajectories, but it's actually invisible from that perspective of this average density matrix. So when people, if you work in open quantum systems, people write master type equations, Lindblad equations on density matrices like this, you actually do not see any of that physics. And this is actually pretty fundamental here. And it tells you that you have to look at very specific observables to actually see this transition. So for example, let's imagine you want to compute the average of some observable, I call O, over trajectories. I'm going to denote this by a bar. So what this is, if you spell it out explicitly, you're summing over your quantum trajectory, so all the measurement outcomes. You have the probability that a given trajectory occurred. And then you just compute, so this is very basic quantum mechanics here, just compute the expectation value of that operator O and that quantum trajectory. Okay, so this is very simple math. The important point is those things cancel out. And so this can be rewritten in terms of this average density matrix. Okay, so So it's a very simple equation, but it has important consequences. So if you're thinking of observables of that type, averaging over the measurement outcomes of the trajectories, you can do everything at once and think of that reduced density matrix. So any observable that as an experimentalist you would just measure and do, average over the trajectories, everything at once, in terms of that, if you don't record your measurement outcomes, would be of that type, and actually you cannot see the transition in this way. In order to see the transition, you would need to consider observables that are nonlinear in the density matrix of the system. So something like this. Yes?
Which side then do you see? Do you see only the volume law?
Right, so this density, this is just a completely mixed state. This is a trivial density matrix in those circuits I consider. And the idea is, if you want, this has some entropy that's just the classical entropy of the measurement outcomes that are. And so this will, this will always be featureless for all of those circuits. So you really have to look inside at those trajectories to see them.
So you don't see the TC and you only see the volume law behavior as well?
Yeah, if you want. So this will remain mixed. Yeah, that's right. Yeah. So if you want to see that transition, the type of observables you would have to look at would be something like this, like a variance over trajectories, for example. So what this changes is now you put a square. So this, it'll still have some cancellation, but now there's a denominator, and now this is something that cannot be written in terms of this average density matrix. So you have to, in order to see those transitions, you have to look at those kind of unusual observables, which are like variances over trajectories. The entanglement entropy is also nonlinear because of the log. So you have to look at observables of that kind. Okay. So now, if you think kind of practically from the point of view of those observables, it should bother you a bit, because if you want to measure something like this, it sounds like, it's at the same time a very fundamental phase transition, but if you look at those observables, they may appear unphysical. And the reason is, in order to measure something like this in the lab, you will need to prepare your system many times in the same trajectory, have the same measurement outcomes. So you will need to prepare your system many times in this state here, where this you have the same measurement outcomes to be able to evaluate this and then do statistics. So what it means is you have to do post-selection on your measurement outcomes to realize the same trajectory over and over. Okay? So this is a post-selection barrier that I wrote here. And of course, that's exponentially hard. So you don't want to do that. Okay? So I should say people actually did this on relatively small-scale devices, and you can see the transition by doing this. But of course, it's not scalable, because if you have a number of measurement n, this will scale exponentially in n. Okay? But there's been a lot of recent efforts recently to go beyond this to, you don't need to actually maybe measure something like this. You can use this information perspective I mentioned, this decoding problem. You can use the measurement outcomes to maybe learn where that transition is, or you can use this feedback that I haven't talked about too much to do something. And actually, there's been a lot of progress, including just this week on the archive. There were things in that direction. Yes.
So it seems like in general, entanglement is a subtle and difficult thing to measure.
Yes. So entanglement is hard to measure. You don't really need entanglement to see this transition. You can see it by looking at. So it's something I haven't talked about. You can couple. You can imagine your initial state as like there's one qubit that's coupled to an ancilla qubit. So this is in the spirit of encoding information in your circuit. So this is a perspective due to Garland's and Hughes. And you can see the transition by just looking at the state of this ancilla. Okay, so you can do full tomography of one qubit. That's not hard. Really, the intrinsic problem is this average over the measurements. So it's not so much entanglement. It's more this idea that you have to find nonlinear observables. Okay. But like I said, this is maybe something we can come back to. But so this is really a big challenge in the field that many people have been thinking about, of finding more scalable ways to think of those transitions. And it's clear there's a lot of information in the measurement record. It's also clear that if you use feedback, you can also kind of go partly around this, but maybe you modify the problem too much. I don't know. Yeah. Okay. So maybe the last point I really want to emphasize, and that I think would be of interest to the other program, are so-called stat-make mappings. Okay. And okay, so far everything what I told you was very general. So you can also wondering how do we know all of this? Okay. And okay, so it's partly from general arguments, partly from numerics. And so you could ask, okay, can we actually have some kind of theory of all those things? And the answer is yes. It's not a perfect theory, but you can do a lot of things. And you can do a lot of things because you have this ensemble of circuits. And this actually helps you. Even though simulating or like having the exact dynamics for a fixed circuit is very hard, dealing with ensembles is actually helpful. So this is, statistical physics inspired, if you want, right? And the basic idea is averaging over the circuits. I'm going to write it in this way. So averaging over the Haar gates, averaging over the measurements is actually helping you. Okay. And you can simplify a lot this problem. So averaging over circuits, though, is pretty hard. It's hard because averaging logs is hard. And it's hard because averaging, so you see this has a denominator. So this depends on the state of your circuit and so on. And averaging denominators is hard. Okay. So if you're statistical physics inclined, you know that averaging logs and denominators is something we can actually do in statistical physics. And the one general trick to do this is known as the Replica Trick. As you take copies of your system, and that helps you average over denominators. So maybe I can illustrate this in this case. So in order to consider a quantity like this, where you have this denominator that depends on the state of the circuit, you can rewrite this in this way, which is quantities, which is an quantity which is obviously correct. Let me write it. So what have I done here? So if I introduced a label k, if you take it to 0, you see it reproduces this when you have a denominator. So now this formula is appealing because if k is integer, you can think that I have a total number of copies, which is 2 plus k minus 1, so it's k plus 1 copies. Okay, so if k is integer, I can think that I have a bunch of copies of my system. Okay? And this actually you can average only if k is integer. So it's kind of a nice trick. Again, it's not new. It was, it's kind of a very general idea. So you take copies where k is integer. The claim is you can do this average. Now you can average over unitaries. But at the end of the day, you want to take k to 0, so you want to find some analytic continuation to k goes to 1. Okay? So this is a very general trick and idea that apply to spin glasses and many other fields, right? And you have to worry about this analytic continuation. So same type of worries you might have in other contexts. Okay, so in the same way, you can rewrite the log using those different quantities. Okay, so this, if k is integer, you can average. And now, basically, what you want to do is you have your system, and you have, I call the number of copies q that is replicated. You have copies, and you want, and again, I'm going to take q to be integer, even though at the end of the day, you'll want to send it to 1. And now average. And the claim is when you do this, there's some math involved that obviously I'm not going to get into here. You can map this onto a statistical mechanics model. And the basic reason is you end up with computing things like this. So you have a bunch of unitaries on each site. On each of my gates is now replicated. You have copies of your system. And you have unitaries from your kets, and you have unitaries from your bras. And you want to average this. The good news is we know how to do this, okay, for various families of gates. And so this involves permutations. So this will generate some permutations. So this is the symmetric group of those replicas. Okay, so if that's obvious to you, it's great. If that's not obvious to you, I'm very happy to explain it to you. Okay, so this is related to show-while duality and all those things. Okay, so but basically they are exact math formulas if you want to do this average. And it generates some degrees of freedom that we call spins. You know, they're like spins of my statistical mechanics model. And at the end of the day, it allows you to rewrite quantities like this nonlinear average or entanglement entropy as things that are more familiar. It allows you to rewrite them as like free energies of those statistical mechanics model. Okay. More precisely, for example, entanglement entropy maps onto a free energy cost of inserting a domain wall in the statistical mechanics model. And that's the last thing I will explain, and then wrap up this talk. Okay. So, not going to write the exact StatMech model, but you know that free energy will have Boltzmann weights. Those Boltzmann weights will be functions of those permutations. Okay, so you have links, you have those permutations, and you have some Boltzmann weights of those permutations. And at the end of the day, in this mapping, computing entanglement ends up being something that's very simple and appealing. So you have your circuits. Now, instead of a circuit, it becomes a 2D StatMech model. So you had time over here, and you had space in that direction. So you run it until time t. And then if you want to compute entanglement, say, in this region, A, what you have to do is something like this. So let me imagine my statistical mechanics model is just an Ising model. This would be the case if you had two permutations. But okay, in general, it's a bit more complicated. But you want to compute a partition function of that kind, where you have fixed boundary condition. You fix all your spins to be up in your Ising model. But in that region A, you fix them to be down. So when you do this, you see you'll create a domain wall between those two domains. That's what I mean by domain walls. And so if you have a ferromagnet, cartoon picture, you should have something like this. Right? Your spins are kind of fixed to be up mostly, but you force the creation of a domain wall here. And in a ferromagnet, this will have finite line tension. So, you know, this will cost an energy that's like linear in the size of that subsystem. Okay, so it's fairly intuitive. So at low temperature in that StatMech model, that's what you would have. And it turns out that the probability P kind of maps to temperature in that StatMech model. So if you crank up P, you get a paramagnet. And in a paramagnet, doing this doesn't cost an extensive amount. So the only thing I want to say here, right, so obviously I'm not going into any detail, is this allows you to map something that's very complicated, entanglement and those circuits with the measurements and so on, to something that's a lot more familiar, which are free energies in some statistical physics models.
Sorry, what is the Hamiltonian of the speed?
Yeah, so it's not a, okay, so I didn't write it, and I'm not gonna. So this is a StatMech model that's defined on some hexagonal lattice. Okay, it comes from doing this average. I can give the details in the end, and you have different weights on those links and on those links, and they're all like class functions of permutations, if that tells you. I'm happy to give all the details after if you're interested. Okay. But there's a big partition function where you sum over all permutations, and you have a permutation on each side. Okay, and the sum Hamiltonian or sum Boltzmann weight. Okay. When you have Q equals 2, it ends up being an Ising model, but in general, it's more complicated. Okay, so you can map this complicated calculation to something that's like free energies, which is a lot more appealing. And so that complicated transition that maps to some ordering transition in this replica language. Okay.
Based on this domain wall picture, can you say something about how the entanglement is scaled with the distance at the critical point?
Yes, that's right. So entanglement scales as a logarithm at the critical point, okay, which you can get from what I wrote here. And the prefactor is not something like a central charge. It's actually related to scaling dimensions of operators that create those domain walls. Okay. So yes, it allows you to say a lot in terms of field theory, in terms of what's going on here. Okay. So this is still a pretty challenging problem. So one thing I'm sweeping under the rug is we still need to do this, and we only know to take that limit in very specific cases. Okay. But I wanted to illustrate that there's this transition, and in the middle, that transition, again, that's for maybe the integrability experts in the audience, is a CFT with central charge 0, which are notoriously a bit hard to tackle. Okay. All right. So with this, let me conclude with something maybe a bit more general. Hopefully that illustrates how you with very basic ingredients of unitarity and measurements, you can get already some interesting phase transition, some interesting phase structure. As I mentioned, there's been a lot of efforts both to maybe realize this in scalable experiments, find maybe more physical ways to probe them. There's this related to decoding problems, and maybe using feedback to do things useful. There's something very interesting on the StatMech side, and there's, I think, some interesting connections to maybe finding integrable versions of this that would have same symmetries where maybe you would be able to take this replica limit. And more broadly, there's been a lot of efforts in recent years, and even recent weeks, to just add, to enrich this story, add competing measurements, maybe that will not be compatible with each other, add symmetries, and realize even more phases, more phase transitions. There's a whole zoo of phases of matter, or dynamical phases of matter in those systems that we're only starting to kind of understand.
That's log A.
Yes.
It's also consistent with numerics, I think?
That's right. Yes. Yeah, it is. Yeah, it was seen in numerics first, actually. Yes. Correct. With this, I'm just going to wrap up, and thank you very much. Yeah. Yes.
Is it possible to do it here?
Not that, yeah. Yes, so the question is whether you can use supersymmetry or in the field of disordered systems, you have different tools to deal with disorder. Replica Trick is one of them. And in particular for non-interacting systems with disorder, you can use this so-called supersymmetric tool. I wish. I've thought about this. No, there's no obvious way around this Replica Trick here. Mostly because it's an interacting theory to begin with, and there's no obvious way that I know of to kind of go around this. But yes, avoiding this Replica Trick would be very nice, but we don't have that at the moment.
Yeah, so if you start with the cluster stage and do the measurement-based quantum computation,
Mm-hmm.
you can try to incorporate this probability into each measurement step, right? So you can consider such a problem. And do you expect some transitions, probability here, or changes of complexity?
Okay, so let me maybe just say a bit more generally, not specifically about the cluster state. So what people have done is to try to, in general, do maybe measurement-only dynamics. That's something that many people in the audience have done, where you would measure maybe stabilizers or different operators in general that will just not commute and will compete with each other, and you can stabilize some states in that way. And yes, you can get different phases. Like I said, you can imagine that this phase diagram is very crude. You can really have many different axes, and like within each phase, you can realize subphases that are either stabilized. They can have symmetry breaking order, they can have SPT order, they can have topological order.
Yeah, so that sounds like a physics question, which is interesting. But is there a way of, is the phase, does it have any implication for complexity? I mean, more in the computer science language?
So, in terms of complexity, the only thing I kind of mentioned, so this has been used in, so you can think that this is some complexity type of transition where, RLO states have the advantage that we can do efficient, maybe, matrix product state type calculations, whereas we cannot for volume law states. So if you think of a general open quantum systems whose dynamics you unravel into those trajectories, and you will have that transition, you can think of it in, if you have a general, also maybe a tensor network, maybe in higher dimension that you want to contract, you can think you will maybe have a type of phase transition like that because it's a non-unitary in general, and which side you're on will have some complexity, I think, implications on how efficiently you can do this. Okay, so yes, Sunwon? Yeah.
So I have a quick comment on
Okay.
the previous question. So there's a work by Aram Hara.
Yes.
They consider 2D shallow depth quantum circuit, including cluster state,
Yes.
and then perform measurement on either random basis.
Yeah.
And then based on these physics, you can relate phase emission.
That's right.
Capability of simulating the sampling of the state using high value.
Yeah. Yes, so I guess Aaron did not talk about this last week, but yes, there's, yes.
Yeah, please.
So what if you actually took away the randomness? Would you still not expect to see like randomness in, for instance, the predictions?
So the randomness in the measurement outcomes, I think, is really crucial to the physics here. Again, the randomness in the circuit, I don't think is crucial. Although it's still a question that people are exploring, right? You fix the circuits and maybe you put measurements, you still see the same physics. And I think the answer is yes, but it's hard to do in practice, I guess. The randomness helps you as well in numerics to kind of see this. But the randomness from the measurement outcomes, from the measurements, I think is really crucial. It's really part of the physics here. I think of it as a disordered problem, really. That's kind of why you need a replica trick, because of those measurement outcomes.
But some of the intuition that you expressed for the area law, wouldn't that still apply? That if you actually had, let's say, like something which...
Right, so there's a question of whether if you consider like unconditioned dynamics and you think of, sorry, I raised my row bar. So if you considered like, say, Lindblad dynamics, maybe you can still get phase transitions in that setup. That would be interesting. In particular, when you do feedback and unconditioned dynamics, that's maybe the type of things you would consider. How they are related to those transitions is another question. So actually, earlier this week, there was a paper by Sebastian Dill and collaborators, for example, that claimed there was a relation between those transitions and transitions that would occur in unconditioned dynamics.
Follow-up to this question. So if you look at any particular trajectory, typically, do you expect to see this transition, right?
Yes, that's right.
So if I just select one of these measurement outcomes and condition.
Yeah, you can do force measurements as well, and that would also be a different transition, but there's still a transition in force measurements. There's in fact, if you consider non-unitary dynamics, and if you consider like a random tensor networks, for example, you would also have those transitions. So they're very general. You don't really require measurements, I think, right? Yeah.
So about this possible symmetries of this random. So if you change the symmetry, do you expect you'll get a different type of transition?
Yeah, that's right. Yes, so natural question is if you add symmetries, like an Ising symmetry, or maybe a U1 symmetry or something, maybe you change the universality class. That would be pretty natural from the field theory point of view. You can also get more transitions, as I mentioned. So that's something I've been working on, many people have been working on in the audience. So if you add like an Ising symmetry, you can have like different symmetry broken phases if you want. That's something Sunwon, for example, worked on, and many others in the audience. You could add a U1 symmetry. There's also additional phase structure there that has to do with how much information about charge do you learn from your measurements. So, there are questions about the transition itself that can change, but there's even more coarse-grained questions about number of phases once you add like those symmetries.
You were saying that finally the randomness of the circuits is not so important. The symmetry.
Right, the symmetry classes are definitely, the symmetries I think will definitely be important, like as you would expect on general grounds. But, the randomness is of course useful, everything I talked about here is based on that randomness helping us, for example. So, yeah.
If the two-dimensional tensor network comes from, say, a higher dimensional tensor network such as the there you have that each layer defines a completely positive map.
Mm-hmm.
Is this complete positiveness affecting the conclusions? So, it's a quantum channel, right?
Mm-hmm. That's right.
Specific additional structure.
Yeah.
Do you think that
Oh, yeah, so as I mentioned, so you have similar phase transitions, for example, in random tensor networks. So if you take a random PEPS, so that's actually something we did kind of earlier. Before thinking about this, at least I thought about random tensor networks before I thought about those circuits. And they also have similar transitions. So even if you take completely unstructured tensors and you think about entanglement, so say you have a random like PEPs, but you put like legs, your actual circuit, your system is at the boundary of a PEPs, but otherwise you contract everything in the bulk. And you say you take your tensors at random, and you ask how much entanglement do you have as a function of, say, bond dimension. You also have phase transitions of that kind.
With the complex conjugate,
yes, that's right. That's right. So I can tell you more about this if you want. Yeah.
All right. Well, thank you very much for a great talk.
Thanks.